Hey, Gary here. When I was in high school, I had a great opportunity to learn digital electronics and programming and some analog electronics with a great teacher I had who'd come from Microsoft. And for many years, I've wondered how I could share some of that experience with others, and I think I've finally come up with a idea. So I'm going to be starting a new series called Turing Complete for Real. And I'm going to be working with the Turing Complete game to do just logic simulation to see how logical gates work. And then I'm going to try and simulate it with another program with actual electrical components on a simulated breadboard. And then we'll see if we can put it on a real breadboard and see the nuance of getting a real breadboard to work. So if that seems like an interesting thing for you, then please follow along and let's get started. And the intro is, as you see here. And it's a pretty simple wire, and they don't really explain much about it. The wire turns on and off. But this actually has a little bit of additional nuance to it. So I'm going to open up another program called CRUMB. And this has a simulated breadboard in it. And something important to know about breadboards is that each of these rows is actually 5 holes that you poke a wire into, and it's connected underneath by a slot of metal. So if you plug in a wire here in 30 and here in 30, then they actually are connected. And then if you connect a wire from here to here, then this one is now connected to this one. And in low frequency electronics, we kind of count wires as non-existent. They have zero length, zero resistance, zero effect on the circuit. So if you want to connect these two together and these two together, and now if you take a wire out of any of these 3 rows, you get the same net. Now if we jump over to SparkFun, they actually have this article about it, about how breadboards are constructed. And here's a real simple breadboard, and if you flip it over, you see these metal strips. And like I said, you plug a wire into each of the holes, it connects it to the metal strip, and all the wires are then all one wire. In this style of breadboard, the center is the same as the red, then these strips on the side with the plus and the minus have a continuous strip all along, and that's for distributing ground and high voltage to your components. Alright, back to Turing Complete. We hit next and we move on to the NAND gate. So they chose to use NAND gates as the base because NAND gates are what most computers are made out of. But if you're actually going to do digital electronics in a class, you would probably use an AND gate instead. But we'll follow along. So we can click these to change the input values. These 2 wires here, they're doing green for a high voltage or a true, and red for a low voltage or a false. And what they want us to do is figure out what the different combinations output on a NAND gate. And so in this case, when we have a false and a false, we get a true output. So we put it there, and then let's So here, oh, still true. Then the other side, still true. And then if both inputs are true, then the output is false. We hit check, and it's correct. So what we can do is we can go into the embedded and choose a logic block. So we're going to choose this 74HC00 quad NAND. Let's zoom in a little bit and say add, and we'll place it. Then we go hit show pins, or we click on it and it shows us the pins. And the first thing you have to do is always connect ground and VCC. And so we can do that here. We're going to get a black. We'll go from ground to this one, and we'll choose red. And from VCC to red, because that's how we've connected it from the 5-volt source here. 5 volts. Red is positive, going to the positive, red. Black is negative, or ground. And now we have our AND gate, or our NAND gate in this case, and we need to output. So let's choose an LED and go from Y1, which is the output for the first NAND gate, and we'll go to here. We can't go directly to ground because it needs a resistor. So we can add a 330 ohm resistor and go from the lower leg of the LED to ground. And the next piece is to add, let's see, active, passive. Yeah, we'll do this one. Do a 4-position switch. So we're only going to use 2 of these, but it has 4 on it. And we're going to connect the bottom side of 1 and 2 to high. And then we're going to connect the top to 1A and 1B. Then we can also add an LED for those. So we go here to here and here to here. And then add resistors again. Here to here and here to here. And you can actually see that this LED is now on. And if we turn the 2 switches, oh, we have to go into interact mode. We put this switch and this switch on, and the output turns off, just like in the simulation. And Turing Complete. So the only way to make the LED on the out turn off is to put both inputs on. Alright, so let's put together the NAND gate circuit on a real breadboard. Here I've got a 3-wide breadboard with the power rail going down the side like we had in CRUMB. And I've also got here on my desk a pretty standard power supply, and I'm connecting the common and 5-volt. So we just turn that on, and then we connect the red and black. So we want red to always be our positive voltage, and black is going to be our ground. I also have a couple examples of other breadboard options. Here's a small one that you can get for pretty cheap. And it's still got the ground and power rails on the side. And this one's another one that I wouldn't suggest getting, but it has on the back, you can see the metal clips and how they're all connected on each row. And the vertical power rails are also there. So the first step is actually just inserting our, in this case it's a 74 LS 00. It's a little different than the HC we had in CRUMB. We'd actually want to get the HC because it's got a wider voltage range and it's a newer chip, faster. But I happen to have these older family LS chips. So the first thing to do is to connect the ground into the lower right and the high voltage to the upper left. Then we want to take our two inputs and connect them to ground. And I've got these nice wiggly wires for that. So now we've got the two inputs. Then we're going to put 3 LEDs from the two inputs and the output. And one thing to note about these LEDs is they actually have a flat part on the red plastic next to one of the legs, and that flat part on the plastic means that the diode is pointed in that direction, so that leg needs to go towards ground. So we'll point that leg away from the chip, and we'll put all 3 of the diodes in. Then we need to add resistors so that we don't burn the LEDs out. I'm actually going to take all 3 of the LEDs and have the resistors go to a single row on the breadboard. And then we can take that row and go to ground on the bottom, and we've got the output lighting up. And that's as we expect. So we've got the 2 inputs are low, and so the output is high. So if we switch to one of them high, we still have inputs of high, low, and we have an output of high. And we swap it, and the other input is high, we still have an output of high. But if we put both inputs to high, we get a low output. So this is the truth table of the AND gate. Another interesting thing about this chip is it defaults to a high input value. So I have to actually ground the input before it recognizes it as a low. So letting it float is recognized by the chip as a high value. And there we have it.